In this video, I'm going to show you an example of how to conduct an actor-partner interdependence model or doing dyadic data analysis in M+. I have example data set here. This is not real data. However, this will show you a really good example of how to construct a good theoretical questions for dyadic analyses and then also how to conduct it. And I have a few files attached with this lecture to help you be able to follow along or do this on your own. If you're using the M+ demo version, you may not be able to include all of the variables I'm including in this example. So just drop a pair of independent variables and you should be able to follow along with this as you move through this lecture. So here is the figure I've developed in PowerPoint to show you what I'm going to be testing in this analysis. In this research question I have, I'm really curious about how relationship satisfaction and partner engagement can predict or influence or how it's associated with depression 1 year later. So you can see I'm looking at relationship satisfaction and partner engagement at wave 3 of when this theoretical data was collected, and then a year later taking depression scores and seeing how those are related. And my hypothesis would be that as relationship satisfaction and partner engagement goes up, depression would go down. Now I want to look at this from a dyadic perspective, and so in order to do that, I take this model here and I break it up between and reproduce it one more time. So I have this model for one set of the partners, the model for the other set of the partners. The actor paths are the paths going from a participant to themselves, and then the partner paths would be going from them to their partner. And this is what that would then look like. I put the partner paths in blue to hopefully make it a little bit easier for you to tell the difference between actor paths and partner paths. So in here I have relationship satisfaction, partner engagement, and depression. And in this data set, it is organized by mothers and fathers. So these are matched pairs, matched couples in this data set. So our next step is to open up the SPSS file. So here's our SPSS file that we have. You can see we have an ID here. And then going down, we have some wave 2 variables. So this is coded as mothers, wave 2, 2 is wave 2, 3 is wave 3, 4 is wave 4. We have relationship satisfaction, and then we have fathers, F for fathers, relationship satisfaction. We have partner engagement, so M is mothers, F is fathers, waves 3 and 4. And then we have their depression scores at wave 4. We have a few other variables we could include here if we wanted to for control variables. So we have work and education and the couples' combined income and also age. So what we want to do is make sure that we have this copied so that when we can do our M+ file, we're ready to go. I've already saved this as an M+ file without variable names written on it, and you can see I have my -99 in here for all missingness. So this is all set to go. We are ready to go into M+. So we've opened up M+ here. I'm going to show you a few different things than you've seen before with how we're doing M+ through the language generator. It doesn't make that big of a difference at all whether you do SEM or SEM with missing data. But I'm just going to click on SEM so you can see what that looks like. So we're going to first click on here and go to find our data set. So there's our dyadic data. Open that up. If we wanted to, we can title this dyadic data demonstration. Go next. So here, I've clicked past this before, but I want to show you this here. So you see this missing value here. If you click yes, this indicates that you do have missing values. And click on the numeric value here. Go to the next screen. This is where you could add in variable names if you wanted to. So I could just add in a quick pair of names to get that syntax started if I wanted to. Go next. I could add one of them over to the use variable list. That'll start that syntax for me. And then here, because I clicked, let me go back, because I clicked yes, I have missing values, and it's a numeric value. I will now have the opportunity to do this. I can say it's the same for all variables and say it's -99. Go to the next. I'm not using any grouping or weighted or categorical variables. I'm using ML as my estimator. You can click mean structure if you want here, because M+ evaluates data with mean structures. However, it does it automatically, so you do not have to click that. We can ask for modification indices if we wanted to at 3.84. We can ask for standardized coefficients, and then we don't need to do any of these other save options. We can hit finish, and then everything is done except for our model. So I'm going to go ahead and get that started. So you can see here we have the title here, right in here, which I can copy and make sure that I save this as the dyadic data demonstration. I'm going to enter over somewhere here because this is a very long path that goes way past 70 columns. And then here are my names R, so these were just placeholders, so I can delete those out. And I copy and paste. Let me go back to here, copy that, and paste those in. So I'm going to make sure I organize this really cleanly for being able to use this better when I'm using everything below, and make sure I can see things clearly and cleanly. So there I have each person's variables, each set of variables on its own line. There we go. And then here are my control variables at the end, and I'll just go ahead and put those all in a line as well. We have our use variables here, which I'm going to add a little bit later, and you can see it's already put in my missing are all -99. It does type as general. That's because when I went to my language generator, I just did SEM. It doesn't matter which one you do. And in fact, if you just still do type as missing, it will still include mean structures because SPS does that unless you tell it not to. So this is less important. We can see we have our estimator as ML, we have our iterations and our convergence right there. Everything else is set to go except for our use variables list, which we need to start our model first. So in our model, again, we are when you do your syntax, you're going to start at the end and then say on and add every variable that has an arrow going into it. You're going to include that over. So what we can see here is both mother's depression and father's depression have the same variables loaded onto it. So we can use our copy and paste function to make this much easier. So I'm going to first grab my mother's and father's depression, copy those. I'm going to add them to my use variable list, go down here to my model, copy those over. So these two I'm going to put on two separate lines because here are my two outcome variables. And then I just want to add in the four variables here that I am using. So I have, they're all wave 3 variables. So we have partner engagement and relationship satisfaction at wave 3. So I can grab my relationship satisfaction here for wave 3, copy that, add it to my use variables list. I'm going to do this on a new line to make sure I am keeping things organized visually for myself. This just really helps me. You don't have to do this, but good organization can help you a lot. So I'm going to go on mother's relationship satisfaction, and then also father's relationship satisfaction. Add that to my use variables list. Father's relationship satisfaction, and then we want our partner engagement at wave 3 as well. And then father's engagement at wave 3. So we have a total of 6 variables that we are using. We have our 1, 2, 3, 4, 5, 6 variables, and we have 1, 2, 3, 4, 5, 6. Now we're doing dyadic data analyses, so I'm going to show you a way to organize this a lot more cleanly because we're going to be doing constraint testing. Now my syntax here is done. This would run correctly to test the model that we have here, because we have mother's and father's relationships, mother's and father's depression loaded onto, so our on statement, each of these 4 variables here. So we have them all here, and this would run and do our model. However, I want to organize this into actor and partner paths because it's going to make my constraint testing much easier. So I'm going to enter these down, and I'm going to use my notes function where I can use the exclamation point and first do my actor paths, and then I will do my partner paths, and I'm going to do that for each of those. So I'm going to take this and copy it, and I want to make sure this is organized cleanly and that it follows both of them. So let's first start with the actor path. So actors is going to be mothers on mothers. So here is mother's relationship satisfaction. I'm going to pull that up here. And then here is mother's engagement. So there are my two actor paths, and then here are my two partner paths. So I have father's relationship on mother's depression, father's engagement on mother's depression. I have relationship satisfaction and engagement in the same order for both of them. So I'm going to do the same thing down here. So my actor paths is going to be, I'm going to start with father's relationship satisfaction. So that way it goes, this is an actor path, so it's fathers to fathers, satisfaction to depression, and it's the same first one up here, mothers to mothers. And then next is going to be father's engagement. So I'll pull that one up here, put it on its own line, so that way we have an actor path, father to father, engagement to depression, and it matches here, so it's in the same order. And then our partner paths are going to be those opposite paths, and I want to make sure that they're also in the same order. So it goes relationship satisfaction to engagement, relationship satisfaction to engagement, and it's mothers to fathers, so that's our partner paths. So now these are matching paths, which is going to make it much easier for me when I go to do my constraint testing. I'm going to do one last thing to prepare myself for constraint testing, and that's adding in all of my mean structures here. I'm going to get this syntax ready, 1, 2, 3, 4, 5, 6, this syntax ready here so that it's ready to go when I want to do my constraint testing for my means. So I want to add in each of my variables into these brackets here. There's mother's relationship satisfaction, mother's engagement, and you can see how because I put these all on their own lines that I'm making this really easy for me to copy and paste. And copy and paste is best because when you just type it in, you inevitably make mistakes. So I'm going to add in exclamation points at the beginning of here because I don't want this syntax in, because this is what I'm going to use when I do my mean constraints. So if you remember, we do our M4, we put in our variable, and then we do in parentheses, we put the letter. Or not the letter, I mean the number. So we put in brackets the name of the variable, and in parentheses we put a number there to tell it to constrain. And you can see a way I do this kind of quickly is just first putting in the parentheses, and then I put in the value, and I can just put in order it 1, 2, 3, 4, 5, 6, and then put in a semicolon at the end here. So now this syntax is ready for me to go when I want to do my fully constrained model. So now I should be all set to go. I have my used variables all entered in, my missingness. I have my names of all my variables listed here in the correct order. I have my model written out, and I have it organized into actors and paths, and I have it ordered in a way so that it'll be really easy for me to do my constraint testing because the corresponding paths are all in the same places in the model. So I'm ready to go ahead and run this and see how my fully unconstrained model looks. And there we go. It went ahead and run. Now this is a just identified model. So if we tested our paths and got our degrees of freedom, we'd find we have 0 degrees of freedom. It's a just identified model, which means the model fits the data perfectly. So our RMCA is 0, our CFI and TLI are both 1, and our SRMR is 0. And our chi-squared is also going to be 0 because there are no degrees of freedom. So I want to set up now an Excel file for me to do my constraint testing, because I need to first determine whether the dyads are distinguishable, and then later doing some further constraint testing to find the most parsimonious model. So I've already started an Excel file here. This is a common Excel file I use to kind of organize myself. And I have the chi-squared, the degrees of freedom, the p-value listed here. I have the fully constrained and fully unconstrained model. And then I'm also going to have my partially constrained model, where I'm going to test paths out one at a time. So if I look at this, I'm going to have, my actor and partner paths. So I'm going to have actor, I'm going to have partner paths, and I have two pairs of them. So if we go back to our figure, we have, depression on engagement. So I'll have depression on engagement, and I'm going to have an actor set, and then I'm also going to have a partner set of paths. And then I'm also going to have satisfaction, depression on satisfaction. So what I've set up here is that I can very quickly, I'll put these italics to make it a little bit more clear, and then I'm going to bold this just to help myself out visually what I'm seeing. So this is where I can put in my chi-squared, which is 0, degrees of freedom are 0 and p-value is 0. And then I can put in the next value here. Now, because the fully unconstrained path has 0 degrees of freedom, 0 chi-squared, the chi-squared difference test is really easy because I'm subtracting from 0. So whatever the value for the chi-squared here is for my fully constrained model is also my chi-squared difference test. So if the chi-square for my fully constrained model is significant, it means that the model has gotten significantly worse, because my fully unconstrained model is just identified, which means it fits the data perfectly. So if my chi-squared is significant on my fully constrained model, it means that my fully constrained model is significantly different from my unconstrained model that I just ran. And that also means, therefore, that my dyads are distinguishable. They are significantly different from each other. And I can continue with the fully unconstrained model. Now, before parsimony, I do want to be able to test if specific matching paths are significantly different from each other. And any that are not significantly different, I want to maintain those as constrained for my final model, because it will add more parsimony to my model. So now this is all set to go. I've saved this as dyadic data for lecture constraint testing. And I can go back to my model here, and I'm going to save this as my fully constrained model. I'm going to take away these exclamation points here, because I am now ready to constrain my means to be equal. And then I just need to test my paths one at a time. So I'm going to go through here and add in all of my parentheses. I do it this way first because it tends to be a little quicker, because the two parentheses are right next to each other, so I can add those in. And then I'm just going to go A, B, C, D, A, B, C, D. So you can see that relationship satisfaction, the partner or the actor paths are both A, and engagement, the actor paths are both B, and then the partner paths are both C, and then the engagement is both D. So I have now constrained my matching set of paths to all be the same. Now, because I'm constraining 4 paths to be equal to each other, this is going to give me 4 degrees of freedom. Every path that you constrain to be equal is going to add a degree of freedom to your model. So I already know when I go to do this, I should have 4 degrees of freedom on my fully constrained paths, because I have set 2 paths to be equal, which is freeing up a parameter, which is going to give me 1 more degree of freedom. So I'm ready to go ahead and run this. I have my constraints all done, And I'm really hoping that I have a significant chi-squared, because that would mean the models are significantly different from each other, which therefore means my dyads are significantly different and they are distinguishable. All right, ran with no errors. So now we can head down and check out our chi-squared, and we can see that it is significant. So it's 19.918, 19.918. And of course, you can see we have 4 degrees of freedom because we constrained 4 pairs of paths together, which has freed up 4 degrees of freedom. And our p-value is 0.0005. And then I can put a little note here to myself that dyads are distinguishable. So I can remember this for my analysis, that they are in fact distinguishable. So now what I can do is go back to here, and I can take away my constraints for my means. So I can either put the exclamation points back on here, or I can just delete it out. I'm going to keep it on here just in case I need it at any point in time. And now I'm ready to test one path at a time and kind of take a look and see if any other paths are significantly different from each other. So I'm going to take away the first 3 and just check my first one. So let's check and see if relationship satisfaction, the actor path, can be constrained to be the same. Now I'm only constraining one path compared to my fully unconstrained model, so I'm going to have 1 degree of freedom. If my chi-squared is not significant, it means that this model is not significantly different from my base model, my fully unconstrained model, and therefore I can keep this constraint on for my final model. So I'm going to go ahead and run that. Oh. Where'd you go? All right, there you are. And it ran just fine, and we can see that our chi-squared is significant. So that means that, so we have, I'll copy this over, so 6.562. So this is this first one here, the actor path, 6.562, 1 degree of freedom, and it was, let me go back here, 0.01 was the chi-square, or the p-value. So this is significant, which means I can put in here, do not constrain. So keep it free. This one we cannot constrain to be equal. So let me go back, and I can get rid of this A here, because that is not going to be the same. Now I want to keep my letters the same that I used before just to not confuse myself. So now I'm ready to constrain my second path, which I'm labeling as B. So the engagement. So this is going to be the actor engagement path, which I have, oh, I did this backwards. I did the satisfaction first, so let me fix that right up. All right, now I'm ready to do my engagement path here. I have it all set. I can run. Again, I'm going to have 1 degree of freedom, and I'm comparing it to my fully unconstrained model. I can go down to my chi-square. There it is there, and we can see that this is likewise significant, which means that these 2 paths are significantly different from each other. And we have a chi-square of 6.223. That's 6.223, 1 degree of freedom, and 0.01 again. So I can have this copy. All right, there we go. So now I know that my actor paths are significantly different from each other. All right, now I am ready to start with my partner paths. So I can get rid of those 2, and now I'm going to test my first partner path. So now I have relationship satisfaction, my partner path on both of them constrained to be the same. I'm going to check my chi-square. And my chi-square, now we have our first that is the same. So this is not significant. So this was, again, for, what do we do here? It was relationship satisfaction partner path is not the same. So relationship satisfaction partner path here, our chi-square was 0.01. And again, we have 1 degree of freedom, and it's 0.92 for a p-value. So this path here, I can constrain to be equal. I can so far do that on my final model. Now I just have one more path to test. So let me get rid of those. And I'm going to test my other partner path here. This is my last one here to see if this one is significantly different. Ready to run that. Go check out my chi-square value, and my chi-square is not significant. So now I'm ready to copy this one in. This was for engagement. It was 0.20 for my p-value, 1 degree of freedom, and 0.65, and I constrain to be equal. Now, because I did all of these separately, I still need to test whether I can have both of these constrained at the same time to be equal to each other. Because I've done these sets of constraints in a series, not all at once, my error has been compounded. So before I go ahead and say, yep, that's my final model, these two are constrained to be equal, I want to make sure I have both of them constrained to be equal. So here I'm going to have 2 degrees of freedom because I have 2 sets of paths that are constrained to be equal. So I have my C and my D, so my relationship satisfaction engagement for my partner paths constrained to be equal. And let's go ahead and run this model. And go down and check out my chi-squared. And if it's not significant, it means I can keep both of them, which in fact it is. So I'm going to create on my Excel file, I'm now going to say both partner paths depression on engagement satisfaction. So this is my final partially constrained model. My final partially constrained model I now have here, and it's 0.225 for my chi-squared, 2 degrees of freedom, and 0.89. So I'm going to put my little note in here that says both paths, partner paths can be constrained to be equal. And I'm going to keep this for later on for when I'm writing up my manuscript. When I talk about doing chi-square difference testing, I have my chi-squares here and my degrees of freedom that I can report in my manuscript for when I did my fully constrained model. And then I can also state that I did this one at a time, testing each path, and then tested the ones that we showed to be not significantly different all together in one final analysis and did a chi-square difference test to determine that, in fact, I could use this for my final model. So this one here is my final model. So I can save this as data discrimination or demonstration final partially constrained model. And now I'm ready to actually look at, let me run it one more time that I save this. I can look at, come on down, my final model fit, and you can see my chi-squared is not significant. If you remember with model fit, you don't want it to be significant. That's good. So my chi-squared looks great. My RMCA is 0, and the confidence interval is 0 to 0.031, and that's with a 95% confidence interval, 95% confidence interval, which means even with my interval, I'm still well below the, I think if I remember right, it's 0.10 for RMCA. My TLI and CFI are both, my CFI is at 1.0, my TLI at 1.05, so those are both fantastic. We want them above 0.9, 0.95 preferably. My SRMR is at 0.004, and that one we want below, if I remember right, 0.08. So we're really sitting good with our model fit. I'm really happy with this model fit. Now I'm going to show you what this constraint testing does. You'll see it here in your unstandardized results. So if we look at our partner paths here, so our partner paths are the ones that we constrain. So we have father's relationship satisfaction and mother's depression. We can see it's negative 0.111. And we can see the corresponding partner path here, so relationship satisfaction to depression, they're constrained to be the exact same value. Same here with partner here that we have partner engagement, negative 0.015, negative 0.015. And we can see our actor paths. So here's our actor paths here and here, that these values are in fact different one from another. That's because we did not constrain them to be equal, because they are in fact significantly different from each other. Now if we go to our standardized output, so we have our STDYX, we can see our actual standardized variable output. So this would be in terms of standard deviations. We can see that for mother's depression, so women's depression in this dyadic analysis, father's engagement here, so the partner path here, is not significant. And because they're the same, we'll see the same thing down here, that this is not significant, mother's engagement to father's depression. So in this fake data, engagement is not significantly associated with partners' reports of depression. So my own engagement is not significantly associated with or predict my partner's reports of depression 1 year later. But so for mothers in here, their reports of relationship satisfaction, this is significant, are significantly associated with depression. So in this one we have at wave 3, mother's reports of relationship satisfaction, as that goes up 1 standard deviation, that is significantly associated with a decrease of 0.16 standard deviations in their reports of depression 1 year later. So in other words, as relationship satisfaction goes up, depression goes down for themselves. So as women here report, or mothers here report, an increase in relationship satisfaction, they're less depressed a year later. And the same thing here with depression. The more that they report partner engagement, the less depression they have. And then relationship satisfaction is significantly associated. So when their partners reports of relationship satisfaction go up by 1 standard deviation, their own depression goes down by 0.04 standard deviations. And then for fathers in this sample, we only have 1 significant result, and that is for relationship satisfaction. So as mother's reports of relationship satisfaction goes up by 1 standard deviation, father's reports of their depression 1 year later goes down by 0.07 standard deviations. So there we have our final model, all complete. I can open up my diagrammer if I want to see what this diagram actually looks like. So I can go here and click on View Diagrammer. That'll open up the diagrammer, and I can see that here, where I can see my 4 variables. Let me pull that back a little bit so it's all on the same screen. And I can show my standardized coefficients, show only the estimates so I get rid of those standard errors. And so you can see here, here's my final model. And I can also say here, like, only show the significant, and this shows you the significant paths. So you can see the significant, here's that 1 significant actor path, and that significant actor path for, oh, there we go. This kind of did it in an odd ordering, so let me kind of fix this so it looks a little bit. There we go. That's better. All right, so here's mothers to mothers, mothers to mothers, fathers to fathers, fathers to fathers. So here are the 2 significant actor paths, and then my 2 significant partner paths in this model. So you've now seen how to do a full actor-partner interdependence model with constraint testing in this video example here. And so you should be set to do your own APIM, so your own actor-partner interdependence models in your own analyses, and ask those kind of questions and do good systemic research looking at the relationships between people in our analyses. Look at the same relationships between people in the same systems in our analyses that we're doing, and be true couple and family therapist researchers.